All right, so eventually I'm going to get to everything that I just handed out. And that's one of the things I've been doing even before the COVID panic struck. I would post everything that I hand out in the course will be in Brightspace or in the beginning of Blackboard. But we've been saddled with Brightspace, so we have to live with it. But everything that I give out in class is duplicated in Blackboard. So if your dog eats your homework, you have another copy. Or for these crossword puzzles, for example, if you go through there and you can do them in pencil, because I know how crosswords are. Just to be sure they're legible, I can read what your answers are. If you need another copy, then it's right there in Brightspace. Okay, so this is the landing page. As long as I don't write on the board, then what I'll do is when I reprocess the video, I'll make this thing whole screen and put me in a little up in the corner. That way you can see it better and follow along with the narration. Okay, so are you familiar with Brightspace?
No, but I've been looking at it.
Okay, good. So you know, if you want to find the course, once you open Brightspace, then you find the course at the waffle, right? Okay, so now that we're here, you can look at your grades here. And shouldn't be any. Well, I'm an instructor. I'll tell you what. I always forget to do this. Let me do it as a student. There we go. Now we're seeing what you're going to see. All right. So if you click on the grades, you're going to just see a list of nothing right now. Just like that. And you should have your homework listed here. They're the first two crosswords. Right? I haven't decided what to do with them. They're definitely going to be extra credit, but I don't know how to apply them yet because this just popped into my head the last week. So I'll figure something out. They will be a benefit of some kind. Okay, so that's how you look at your grades and assignments, of course. For the lecture, the only types of assignments you'll have will be the extra credit, the crosswords. So you can find those here. You can also find them in the content, which is where I'm headed next. Homework doesn't show up in assignments. All right, I'll show you where that is in just a second. So you go to content. There we go. Come on. It's not cooperating. Try it again. There we go. Okay, well, that's where I left off. So let me go back up here and I'll go to table of contents and that'll start us from the beginning. We have a new contact with Cengage. It's not, what's her name? How soon we forget. But this guy, they're doing some shuffling at Cengage, so we've got a new contact here, is John Sayall. There's his contact information if you have any trouble with Cengage. Then here's the course schedule. I put it in as a separate page, so you won't have to dig through your syllabus to find the schedule. And this is a good opportunity to discuss the schedule because that's really the meat. That's the focal point for knowing what we're going to do when things are due. Okay, I've color coded a little bit differently this time. These I've got a column over here on the right. You'll see is a duplication of the labs that we're going to be doing in the days they are, so we can cross-reference with the lecture. So you'll see that on these days that I've got in lavender here, those will have labs. Those will be on those days, we'll do something in here for the lecture and then we'll go in the lab on that day. That also helped me avoid conflicts because I don't want to have any exams on lab days. And I don't think I do. If you see anything that doesn't look right, call my attention to it because I make mistakes. So there are the labs on the right, and you'll see highlighted in yellow are the exams. Right, so you got all those exams. We've got one day that we're off on July 4th, so we won't meet on that day. And then you'll see also the activities and lessons that we're going to cover here on the right. So those days when we have a lab, we're going to have a review session. This would be material that we covered the session before, and it's going to move pretty quick. Right? If you thought that the regular semester was fast, this is faster. We've only got 10 weeks to cover an entire semester. So it's going to, fortunately though, you probably all only have this one course, or you have more? You have two. Okay, what's your other course? Oh. Okay, I enjoyed micro, but it is a lot to.
Yeah, I saw the layout and I thought this one's going to be the meltdown course this go around.
So that's the schedule, and you'll notice also up here at the top is the link for the course if you Zoom. Right. I've got it in 2 or 3 different places, and the schedule is one of them. You can get to it through Brightspace, of course, and I'll show you where that is in just a minute. But homework and the exam are due on the same day. And have you ever done Cengage homework?
Yes.
Okay, good. So the one caution that these guys already know is when you sign up for the Cengage homework, you do it from within Brightspace. Okay, have you already done that?
Yeah.
Oh, good. Then I'll shut my mouth and move on. Okay, here's where you get your book. There's the syllabus, and my schedule is right here. And so my schedule is pretty slim this summer, as it should be. So I've got this course, and those are the days for this course. And then I've got Chem 101 and 103 I'm doing online, because I only have 3 students. So it didn't make sense to try to do a face-to-face. I don't think they even wanted a face-to-face either. Anyway, that's my schedule. And this link up here is my personal meeting. So I don't have any office hours in the summer. They're not required. But if you want to Zoom a meeting, if you need some tutoring or for any reason, then we schedule a meeting, and that's the link you'll click. Okay. So that was my schedule. And now let me call it syllabus. Come on. There we go. So I'm doing this just so it'll be in the recording. Right? You guys have a hard copy. Everybody else knows that all my contact information is here on the left in that blue box. Okay. So you can find me in this office right here, or you can do by appointment. You can do, there's my ID. So if you want to do it from your phone, you need the Zoom app on your phone, and then you just punch in that meeting ID, and you can connect if we have a meeting scheduled. There's no passcode associated with it. Why is it still there? I'm gonna have to talk to Nate about this computer. It's been acting, ever since the last update, it's been acting kind of wonky. Okay, there it is officially. It's a traditional course. So we're going to meet face-to-face in the lecture and lab. There are the times, and there's the required text, the Cengage thing. If you want a hard copy, there are the particulars on the hard copy. You don't have to buy one. Right. I think Cengage will still send you a loaner if you want, but you can find cheap used copies on the internet. Easy. They're fairly cheap, I think. I wouldn't say dirt cheap, but they're cheaper than the new ones.
Hard copy on Amazon for like 88.
Really? I thought they'd be less than that. If you go back to a 9th edition, they might be cheaper, and a 9th will work.
Well, I got it last semester, so I already have it.
Oh, okay, that's right. You told me that. You're going to need a scientific calculator. You have one? Okay, good. If you take your exams online this semester, it's going to be proctored by Lockdown Browser, Respondus Monitor. Okay. I'm not going to do the PDF files this semester. I've got it set up so that the exam will be in Brightspace, and then when you click on the exam, it'll bring up, if you've done this before in other courses, it'll bring up Lockdown Browser, and you'll have to go through some steps to prove it's you. So you'll need your webcam and microphone, and if you're going to Zoom any of the meetings, whether class meetings or personal, you're going to need all this stuff anyway. And if you have a laptop, you probably already got it built in. Other materials, since we don't have a lab today, I won't be discussing the lab materials, but heads up, if you don't already have a lab coat, you need to get one. Like this, knee length. Okay. While I'm on the topic, you're going to need a brand new, unused lab notebook. So if you don't already have one, I brought some with me. Only the price has gone up. Inflation. If you don't want to go to Walmart or wherever and try to find one, I'll show you what it looks like. Well,
Can I get one off you Thursday, Dr. Blah? Can I get one off you Thursday?
Oh, sure.
Okay.
I just thought I'd give you guys a chance to start setting them up. You know how to do that. They look like this now, and they have to have quadrilined, right, and bound, no loose leaves. First thing you do is put your name, course, and that number in the semester on the cover, and then you number. Start from here, 1, and then the next page, left facing page will be 2, right facing 3. So all right facing pages are odd numbered. You go all the way to the end, and there's in the neighborhood of 200 pages, I think. Do it, and it's always in ink. Okay, if you need one, they're here. Okay, we don't need to labor that one. You can read this at your leisure. Regular exams. If you come to class, you get a paper exam, and I'll grade it before you leave, so you'll know where you stand immediately. There's your homework. And since you're already signed up, I'm not going to worry about that one. Grading scales, I think this is similar to the last semester. Oh, no, that's a mistake. I'm pretty sure there's no final exam. There's not time for them. Right, that's a mistake. So what you do, the chapter exams, instead of 55% will be 70%, because there's no final exam. Okay, I'll correct that and put it in Brightspace in its proper form. I'll make myself a note. Better do that. This is out and this is 7%. Okay. So you get credit for showing up, either a Zoom or face-to-face. Homework is 20%. And I have a 10-point grading scale. So if you get 90 or above, you get an A. I communicate using the your New River address. So, I mean, it's okay to contact me with your personal email address if you want, but when I send something out, it goes on your New River email. So be sure and check that at least once a day. Or if you have your phone set up like I do with multiple accounts, right? They'll announce themselves when one shows up. Okay, so there's a schedule again. We won't have to labor that. I have to put this in here, administrative withdrawal procedure. If I don't see you and you don't contact me for 2 weeks straight, I have to let the registrar drop you from the class. I'm gonna let you read this other stuff. Let's see. The extra credits, everybody gets an equal opportunity. And the only extra credits I have this semester, standalone extra credits, are the crosswords. Exams will still have bonus questions. So you have access to those too. And they usually help. Let's see. There's some other details in here. I'm trying not to go more than an hour with the introduction so I can get into chapter 10 today. That way we won't have to rush through the next. We've got I built one bonus day, and I mean, not bonus, but buffer day. Yeah. So we can get a little bit of chapter 10 today. We can get Thursday, we can get finish chapter 10 if we need to, chapter 11, or we can slide into the 30th of May to finish them off before we do a review on June 1st. So I gave myself a little bit of extra time at the beginning, but after that, we're going to move at a lightning clip. Okay. That says office hours, but I don't have any. That's how you connect if you're doing it from your computer and you don't connect through that link. By the way, if we schedule a personal tutoring or a meeting of any kind, what I usually do is respond with the time and date and a link so that you can just go to the email and click on it. All right, let's see what else. This is stuff they make us put in here. This is an appendix. All right, so this is your homework appendix. Look to that if you have questions, or contact me if you have other questions. It won't look, these won't be the exact same modules in the homework because I use the same one for everybody. Here's your lockdown browser, Respondus monitor procedures. One thing about Brightspace this time is nice is that the first time you go in and there's a practice test. I'll go back and show you that one. There's a practice test to be sure that all your equipment is working. The first time you click on it, it's going to check to see if you've got lockdown browser installed. And if you don't, then it takes you to the installation page, and you finish that, and then you continue. And once you've done all that, then every exam after that shouldn't give you any trouble. That's why we put the practice test in there, to be sure that your equipment's working right. And if you're using a Windows or a Mac, it might be a little different. I've enabled the ability to use a tablet. You can use a tablet. I don't know if Apple products work as well. Does anybody in here use Apple? No.
Yeah, I have a Mac.
Okay, so it worked okay for you, didn't it?
Well, we didn't use the lockdown browser last semester. Okay. I don't think I can use that.
Let us know if you're having trouble.
Okay.
But the instructions for Mac are included in this appendix.
Okay.
There's an iPad. So Yeah, I know it's supposed to work with,
Works for iPad. It should work for a Mac then.
yeah,
Okay, cool.
okay, I think that's the last appendix. There's your practice test. Right. Come on. And some instructions to follow that. And here's zooming into the class. You can do it by a Brightspace connection, or you can do it from within Brightspace. It works both ways. You just need different instructions. And here, if you're zooming in, this tells you how to enable side-to-side mode. So you can shrink my image and stretch the shared image if it's more difficult to see. And that should be the end. Should be, yeah, that's the last one. Okay, was I going to do something else? Go back up here. I think. There's the schedule. They haven't given us a final exam schedule for this class. I don't even know if they have one. So we'll just have our last exam on chapter 18 on Tuesday. And there's no lab on Thursday, so you'll be done then. So we have 6 labs, right? Should work out okay. And that's it. Any questions about this part? I know what it was. I was going to go back to the Brightspace course. Here we go. All right, so down the left-hand side, you'll see these others. There's your ebook. Nice thing about ebooks, I know I like paper, but ebooks are good for searching. If you don't have a PDF reader, these are 2 possibilities. Right? They're free, right? And according to the latest versions of the Acrobat reader, is you should be able to take a form and fill it in, which actually won't be an issue this time, because I didn't create forms for the crosswords. I couldn't figure it out. So the crosswords, if you don't get one, you've got to print it out. If you don't have a hard copy from here, print it out, fill it out, and hand it in. Or if you submit it in Brightspace, you got to photograph it or scan it. Same as the homework and exam. Yeah, you can turn them in early if you want, but they're due same time as the exams. Okay, readers. What this one is? Why is it giving me that? It's giving me that funny. Okay, this is just extra stuff from Cengage to help you process it, get familiar with the homework. Learning modules. This is the business end right here. Come on. There we go. Learning modules. Okay, this first module, let's collapse them all so we can see them. This is aggravating. I bet it was that last update. Last Windows update. There we go. Okay, this practice test is the one that you'll take. You can take it anytime. It doesn't matter if you get the questions right or wrong. You're testing your equipment. So once you've done that, then you know your equipment will work for all the rest of them. And here's exam 1. And all of the modules are arranged exactly the same way. Here we have chapter 10 and 11. Are these? Hold on a second. Yeah, okay, click on that one, and now you get the PowerPoints. PowerPoints come in 3 flavors, right? These guys already know that. You got a bona fide PowerPoint slide set. You got it converted to PDFs if you don't have access to your Microsoft Office, or you can click on this one and it should come up like this. Oops, I need to fix that. Y'all remember that? The scrolling monster. Okay, I can fix it. I just haven't done it for chapter 10 yet. But that way you can see it in the browser when I get it fixed. And the if there are any embedded videos or animations, they're also there. They don't show up in PDFs, but they will show up in the HTMLs. All right, so that's another job I have to do, get that fixed. Okay, let's go back. Let's see, there's no breadcrumbs here. Sometimes they got breadcrumbs and sometimes they don't. All right, content. Work my way back. Okay, let's do it this way. PowerPoints, then reviews. Right. So the review documents that you picked up here are also available here. You've got the PDF file for the review document. I don't print out the key, but the key is here to check your answers. If you want to notice, they're set up exactly like an exam will look. So you can take them as if they were an exam and then check yourself and then go back and do it again, do it again, do it again. And then here's the worked problems, that handwritten copy that works every problem in the review document. So if you get stuck, go to that and see if that triggers rings a bell. And then when we come to class on review days, bring those problems with you and we'll solve them. We'll try to figure out where the sticking point is. If you don't have any, then everybody else knows that I'll just start talking. And I'll pick out some representative problems and we'll go through them. This is the extra stuff, how to find the edge of a unit cell, body-centered cube. We'll talk about that in just a few minutes. But these aren't essential, right? They're just extras. This is where you want to focus your attention on these review documents. If you are comfortable with the review document and every problem in there, then you'll have no problem on the exams. Let's see, chapter 11 is going to be built the same way. Get to your homework, you click on the homework there, and here's your chapter 10 homework, here's your chapter 11. This takes you directly to that chapter homework in Cengage. If you click on this and you haven't registered yet, then it'll take you through the registration process. But if you're already registered, it recognizes you that you're coming from within Brightspace, and you won't have to, I don't think you have to sign in, do you? No, you shouldn't have to sign in again.
No.
Okay. All right, so what else? Video archives. Now, everything we do in class is videoed. I process it for dead air. I cut that out. Sometimes I cut out mistakes, big boo-boos that I make, or I may put a comment at the bottom. But once I process them, I upload them to YouTube and then put the link in here. And for, let's see, learning modules, here's the intro, chapter 10 and 11 lecture. So it looks like I did both of them on the same. Did I do both of them on the same day? There must have been a lab day, because this would have come from this class, right? Oh no, I'm sorry. What am I thinking? The last time I taught it, right? So this is January 23. What I'll do is when I get a current one and post it, I'll move this one down into the archives, and same thing with review, and it'll go down in.
I always saw the older videos.
They should show up.
I never saw them because I even double checked the dates to make sure that I wasn't reading them wrong. I never could find the videos from
Well, you need to tell me that so I can fix it. Okay. Well, I'm in here as a student and I'm seeing them now, so maybe that was peculiar to 101. Let me just go back.
Remember that when we were saying, was it January or something?
Yeah.
Like I could find
Okay.
the ones from the previous semester.
Okay, this was our course. This was 101. Let's let me in there as a student. Okay. Let's get this. Come on. Okay, we'll go down to module 1. It started at the beginning of the semester. You had trouble all the way through the semester. Okay, so 1. Okay, there's the video. There's the video.
I think the only one I ever saw the current to was, there was one, I think it was when we had to leave early and you said because of water or something.
Yeah.
And you sent us the link where you went back and finished the review.
Okay.
Where you sent us that direct link. That was the only current video I ever saw.
Well, let me see if it. Yeah, there it is. That's chapter 2. There's chapter 1. There it is.
I never saw those. I would see the ones from the fall.
My name is Bly, Dr. Bly, and this is CHEM101.
Okay. So that's. I guess that's all right. I don't know what the problem was. Were you trying to get in there before I had a chance to process it, maybe? No? Okay. I'm stumped. Okay. Get this thing out of the way. Let's close that. Go back here. Let's go back into 102. Okay, if it happens again, let me know. Because I don't know, have any idea what the problem is. But we'll work on it. We'll fix it if it's giving you. And the same goes for everybody. If you have any trouble in here, let me know so I can fix it. Okay, but all the old videos are here in the archive, and there are lots of them. The older they are, probably the worse they are. I've been learning as I go.
Still sounded helpful.
Okay, well, that's good. I know to keep them in there then. Let's see. All right, so every one of the modules, the exams modules are going to look exactly the same, right, all the way down through chapter 18. There's some supplemental documents in here. In fact, I don't even know what I've got in here. Oh, there we go. You can take a look at these. They're looks like they're specific to different topics that we're going to cover through the semester. So you naming. Okay. Have you had a chance to look at the syllabus and see if there's anything in there that you've already covered in previous? I assume you're transient, right?
Yeah.
Okay. And where are you coming from? Okay. What I can do is give you a copy of 101 so you can see if we've already covered that.
Yeah.
Okay. Right. Remind me when we get finished here, and I'll pull you out a copy. Other things from first semester. Periodic table. I pulled this up in Chem 101 and had all my students memorize, learn the symbols for these elements. Come on. Oh well. There it is. Okay. So if you pull this one up, you'll see which ones I expect you to know. They're in the red boxes. Here, all over there. About half of them. And I've identified the ones that are diatomic in the blue. Right. You probably already learned those. I think they're pretty thorough over there, aren't they? Yeah. They're probably more anal about chemistry than I am because I wasn't trained as a chemist. I just have lots of graduate chemistry courses so I can teach it. But their people are probably diehard chemists, right? And they look at the world a little differently than I do. I come from agronomy, crops and soils. So I'm more down to earth than those guys. Although there are some exceptions. You'll run across a real person in the chemistry every now and then. We used to have one, in fact, at Greenbrier campus, Dr. Dynack. He was real. He was also an organic chemist. They're kind of strange ducks. You ever met organic chemists before? Yeah. They keep a really sloppy kitchen. If you ever go into a chemistry lab, an organic chemistry lab, it's pretty messy. So is their stock room. Anyway, I digress. These guys already know I do that a lot. Okay, let's see. If you use the textbook and look at those problems, in fact, Cengage, the EOC, the end of chapter problems in Cengage that you work your homework, are taken from the textbook end of chapter problems. Right? You may have noticed that, maybe not. But if you find one of those and the hints that they give you in the homework don't help, then another place you can go is to this item right here. These are the solutions for the 9th edition end of chapter problems. Right? I didn't point that out last time, did I? Okay, I should have. I can just get it to come up. Here we go. So chapter 10 solutions. There we go. So these are I don't know if they're all of them, but there are a lot of them right here. Solutions to the chapter 10 end of chapter problems. And if they, if you have a problem with the Cengage homework, maybe run over here and check, see if you can find it in here, and it'll give you a solution to the problem. I'm just telling you how to make 100 actually. They're my breadcrumbs. Come on. They work about as well as the other. Okay. I'm about out of time for the introduction. Let's see. The rest of the stuff is extra. Right? It's going to be common to any Brightspace course that you run across. We've covered everything that I've put in here that's special to this course. Right. Any questions so far? All right. In that case, I'm going to stop this share, and then I'm going to go open up chapter 10 PowerPoints, and then I'll share them. Thing got moved around. Chapter 10. Here we go. Okay. Anytime now. There it goes. All right. So let me go back here and share. That might be showing me something I can't see behind it. There we go. Chapter 10. All right. So let's slideshow. Come on. There we go. Okay. You guys see that all right on Zoom?
Yeah, everything looks good.
Okay, good. All right. I'll get my utensils. Good. All right. Chapter 10, it's on liquids and solids. You might be wondering, we already covered that topic. We talked. Actually, we didn't. Not in this kind of detail. We're going to look at liquids and solids from the atomic molecular level, how they're built up. And we're going to go backwards and forwards between molecular or covalently bound compounds and ionic compounds. So be flexible, right? I don't want to give your brains whiplash. But when we talk about intramolecular bonding, that is within the molecule. So now we're talking about covalent bonding. The bonds that hold the molecule together. And they're formed by sharing. Then these molecules can also interact. And they do so in several different ways, which are essentially electrostatic in nature. In other words, a difference in charge between negatives and positives. They don't have to be complete ionics, like sodium chloride, a complete sodium ion or complete chloride ion attracting. That's one way. But with these molecular compounds, their interactions are more transitory, and they're not full strength electrostatics. They're somewhere below what we would consider ionic. And to do that, we need to identify whether the molecules have a dipole. And we did that last semester with a VSEPR model and that kind of structure. So we're harking back to those days where we looked at molecular structures and whether or not the molecule had a dipole. If it does have a dipole, then, and it's a pure substance, then you can rationalize their interactions. I like to use water because it's very simple. Right? We know that the dipole on that bond is going to be this way, and the dipole on that bond is going to be this way. So overall, dipole is like that. So if you've got pure water and they encounter one another, then you're going to have a slight negative charge up here, slight positive down here. Let's balance it. So it's two there. Then when another water molecule shows up, it's going to align itself something like this, maybe, right? This slightly negative and this positive here. And there's going to be an attraction, right? That's a dipole-dipole attraction. In fact, that's a special kind of dipole that's called the hydrogen bond. Right? Did you guys cover that yet? Mm-hmm. You did? Okay, so some of this is going to be old. So that's, if the molecules have a dipole, then they will orient themselves so that they have if this water molecule approaches with hydrogens, then it's going to repel and probably rotate until it finds the right attraction. And you're going to get a dipole-dipole forces imposed. And those contribute to physical properties of the physical and chemical properties of the substance. If you have the opportunity for this dipole to form, I'm stealing some of my own thunder. The boiling point is going to be higher than you would expect because you've got these attractions that are holding the molecules together. And in order for a substance to boil, you've got to break those bonds and convert it from a liquid to a gas. So these dipole interactions will increase the boiling point, for instance. Then we have other types of forces when you don't have a dipole available, but we know that there are some forces available because we can cool the substance down and it will phase change. Right? It'll go from vapor phase to liquid phase to solid phase. Then you know that there are some forces interacting, some intermolecular forces that are at play, but we can't attribute them to this electrostatic, this permanent electrostatic interaction. Right, so we have to be creative. In fact, this guy in London did get creative, right? And we'll talk about that in detail in just a minute. The other point to take away from this is the relative strength of the intermolecular versus the intramolecular bonds. And this is not purely, but it's logical. The intramolecular bonds holding molecules together must be stronger than the intermolecular bonds, the bonding between molecules. If the intermolecular forces were stronger than the intramolecular forces, then they would be sufficient to rip the molecule apart. It's just that simple. So we know that the forces holding molecules together must be stronger than those that are holding separate molecules together. Okay, this is hydrogen bonding in water, and it's fairly extensive, but it doesn't have to be, they don't have to sit there and say, okay, I found a partner, I'm going to stay here. No, they'll move on. All right, and the more kinetic energy that's put into the substance, for instance, by heating it, the shorter the time that they spend together, and they'll move and find another partner. But those forces are always there. They just kind of switching, right? And if it's a liquid, you know that the molecules are free to slide past one another. So they interact for a split second and then they move on. Okay. I stole my own thunder on this one. Intramolecular bonds are stronger than intermolecular bonds. How do we know? There it is in blue and white. Phase changes, okay? When a substance changes from a solid to a liquid to the gas, the molecules themselves remain intact. This is a physical change, and we studied that at the very beginning. Physical changes occur when the phase changes, or any change in fact, as long as the substance retains its chemical identity. In other words, if it's water as a solid, ice, it's water as a liquid, it's water as a gas. Any of those changes are only physical. And they're due to those forces between molecules. Right. If we could see the molecules of the atoms in these different phases, then they would be something like this. Gases, very high kinetic energy. The molecules are moving very fast and they're very far apart. Liquids, they're much, much closer together, but they're not regular. Right? They're free to move past one another. That's why they need a container, because they won't hold their own shape. Solids hold their own shape because they form regular structures. Sometimes they're crystalline structures in which they're repetitive, and sometimes they're amorphous, which means that you can have, if it's a pure substance, of course, they can be any arrangement whatsoever, as long as they hold their shape, then they're solids. Or they can be regular, right? And so you see repeating units from here across here in 3 dimensions. But this also tells us that solids and liquids are pretty close to the same density, and gases are much, much lower density, mass per unit volume. The rule of thumb is when you go from a liquid to a gas, you increase the volume of a given mass by about 1,000 times. And that's just a rule of thumb. I mean, it can vary all over the place, but it's useful to know that. So as we add energy to a solid, then the motions of the molecules start to increase. Of course, if they're in a solid structure, right? They're not going to be moving from here to there. They're going to be vibrating, right? And as you increase the energy content, they vibrate even more until they finally break those intermolecular bonds from a permanent status to a temporary status, and then they move past one another, and they only interact temporarily as they change the shape of the entire mass. There's more disorder. We studied that last semester, didn't we? Entropy. Did we cover entropy? I think we did. Where's that coming? Maybe that's this semester. You guys didn't cover entropy, did you? Oh, that's later. Excuse me. Okay, we will get to that. But they're more disordered as you go from a solid to a liquid. And definitely from a liquid to a gas, you add so much energy that you break them into independent molecules, and they're moving. If they do encounter one another, their attraction is, I mean, not just temporary, it's fleeting. That's why we can treat gases, a gas, water vapor, hydrogen gas, carbon dioxide. We can treat all those gases from a gas law perspective as the same, because there's so much distance between them and they don't interact that often. The energy is so high, if they do interact, if they do come close enough where the dipoles do interact, it's so temporary and their energies are so high, it has little effect overall. So that's why a gas is a gas is a gas. Right? It just doesn't matter what it is under most circumstances. Okay, so here we have a chart of densities, and this came straight out of your textbook, right? Water, we're using water as an example. I think it's a point of discussion, but water is not typical of solid, liquid, gas transitions, because the density of solid water, ice, is lower than the liquid. Right? Did I show you guys that last semester? Why that is? As long as you have liquid water, then they're free to move, and they optimize their arrangements so that there's very little unused space. There's always unused space, but they minimize that with their interaction, because that means lower energy, right? And all systems tend toward lower energy. It's more stable. But when we form ice, when we cool it down, then they start to arrange themselves into a regular crystalline lattice. And the arrangement is hexagonal. Right? So you may have an oxygen here, and then the hydrogen is over here. And then there's another hydrogen here attached to that oxygen. Well, this one is going to be, so we got another oxygen here, and a hydrogen there. This one's going to be one of those intermolecular bonds. These are the intramolecular bonds, and then there's another hydrogen over here, and there's another hydrogen over here, and there's another hydrogen over here. So they arrange themselves in this hexagonal structure. That's why snowflakes have 6 sides. It's that molecular arrangement that gives them that structure. And when they do that, what they do is they sort of open up this space in the middle. Right? They add volume to a given mass, and that's why the density of water, solid water, ice, is less than liquid water because of that structure. And it's a good thing it is that way, right? We go through winters and lakes and oceans freeze over, right? If the solids were more dense than the liquids, what would happen to the ice? To the bottom. Insulated, right? It would just stay ice. And then we'll freeze another layer. Pretty soon, all the oceans and lakes would be solid ice, right? There'd be no liquid water on Earth. So, as it is, since solid or ice is less dense than water, it floats, right? So it forms this layer, and it insulates the underlying layers, right? So the fish and aquatic animals can go deep and not freeze to death. And then when summer rolls around, right, it melts and you're back to a different ecology. All right. So I wasted enough time on that one. That just explains the difference in density. Of course, gases are much, much lower simply because we've spread those molecules out. Right? Density is mass per unit volume. We add all that volume, the density goes way down. Now, in this case, my rule of thumb was fairly close. Right? We went from a 1 to 3 times 10 to the minus 4. Right? 1, 2, 3, 4. Versus 1 is how many orders of magnitude? Well, 1, 2, 3, 4. 4 orders is 1,000. No, 3 orders is 1,000. 4. All right, so it's 10,000. All right, so I was right about one thing. Rule of thumb is just that. It's a rule of thumb, and it varies all over the place. It works better for cryogenic liquids like nitrogen, liquid hydrogen, liquid helium. Those, it works better for those than it does for these hydrogen bonded type. Okay, these dipole forces. You have to have polar bonds. Remember how we determine whether a molecule is polar or not. The bonds have to be polar. And then the geometry has to be such that those bonds are not all canceled out. Right? If it's a regular structure, then the polar bonds will cancel out and your overall molecule will be nonpolar. But with water, we just showed that water being bent, right, instead of straight, if it was straight, then those dipoles toward the oxygen in the middle would cancel out. But since it's bent, the vector addition of those dipoles is an overall dipole for the molecule. Carbon dioxide, though, is a straight molecule. You'll remember that one. If I draw it right this time. Lewis dot structure, right? The dipoles like this and like that. Equal and opposite cancels out. Carbon dioxide is nonpolar. So when it forms, when we cool it down enough to make liquid or solid, like dry ice, then we have to cool it down a lot more than we would for water to make ice because the bonding is not strong enough. So these dipole-dipole interactions are only about 1% as strong as covalent or ionic bonds as a general rule. Right, so they're very weak by comparison. You can also have, and when we talk about ionic bonds, of course, we mean like something like this, like that. You get those, and actually, they don't form molecules. Right? Remember, they form crystal lattices. So this is going to have another chlorine down here, and one here, and one here, and then there'll be one here and one inside the board, and then this one will have sodiums around it. This one will have sodiums around it. So it's a network. But with dipole-dipole interactions, you can have either two molecules that are polar, or you can have molecular substance forming a bond with an ion like that. So if we put sodium chloride in water, then it's going to orient itself like this, right, and form a bond there. Okay, so you can have ion dipole interactions also. Hydrogen bonding is a special kind of dipole-dipole. And what's required is hydrogen, obviously, and hydrogen is covalently bound to a very electronegative element, usually oxygen or fluorine. Nitrogen also works, too. So we find it with fluorine, oxygen, and nitrogen. The others are not electronegative enough to distinguish their bonding as hydrogen bonding. So you could get hydrogen bonding with ammonia. That structure there, like that. Right, so we would have a dipole this way here, a dipole here like this, a dipole here like this. And then with this lone pair also, you get an extra negative. And ammonia is dipole, is a polar in that direction. And it would form, this would be the negative side, this would be the positive, and they would orient themselves like I showed you with water. And these would be hydrogen bonds. They're typically the strongest of the dipole-dipole type bonds. Okay. Now, for those non-polar substances, how do we explain the way they bond, the way they interact? It's a process called London dispersion force. As opposed to a permanent dipole that you would have with, say, a water molecule, the London dispersion forces show polarity on an instantaneous time scale. In other words, they appear and they're gone. Right? So they're not as strong. They're only temporary, but they do exist. They usually occur and they're stronger with larger atoms and larger molecules. And the reason for that is, let's see, one example. Let's say xenon. All right, xenon 54 is a huge atom, very large. All right, so it covers maybe a space like that. But for helium, it would be very small. One thing we know about electron distribution in atoms and molecules is that it's always on the move, right? We think we know, and we talked about atomic structure when we did our periodicity, and we drew the electronic structure of atoms, but we didn't emphasize so much the fact that these electrons, well, the Heisenberg uncertainty principle says we really don't know where they are. Right? If we say anything about their position, where they are, then we can't know anything about their velocity or energy. Right? And we're more in tune with energy, so we use a probability for where we might find the electrons, right, in those orbitals. Does any of this sound familiar? We did do that, didn't we? Yes, we did. Okay, so the idea here is that the electrons are on the move, right? And they temporarily, you might get a distribution of electron density over here, and that would leave this one deficient. Right? And this only happens on the femtoscale, right? Instantaneous. Well, what does that do? Well, when that happens, any xenon that's nearby will be influenced. Let me erase this temporarily. Any xenon that's nearby will be influenced by that distribution, and it will tend to push electrons away from here and make this one slightly positive. Right? So when it does that, it sets up the opportunity for intermolecular bonds. Okay, and these are the London dispersion forces. We know this is true if we look at the boiling points of the noble gases, right? And we do that because they don't typically form chemical bonds with anybody, definitely not with each other. So that sort of eliminates that fly in the ointment. As they get bigger, their boiling points go up, they increase. You have to get them warmer to make them boil. Now we're talking about things down in low kelvins, right? Helium boils at 4K. It's the coldest pure substance that we can isolate. And then neon has a higher boiling point, and then argon higher, higher, higher. And that's due to these, because they're so large, they have the tendency for redistribution of electron density on a larger scale as you get bigger. Now, this can happen with molecules also. The reason I put helium up there was to show you that with the smaller ones, you don't get as much opportunity for redistribution of electrons. First of all, you don't have as many. So if we have large molecules, like say hydrocarbons, right? Hydrocarbon is just what it says. It's only got carbon and hydrogen, period. And now I'm talking about aliphatic, which is an organic term, which means straight chain. Right? So if you have the simplest is methane, right? Just one carbon. So it has a given boiling point. And then if you put two carbons together, right, then it has a higher boiling point. And you can just keep going with propane. Let's see, A. Butane, right? Those butane lighters. This is the stuff they put in there. Let's see, 4, 5, 10, 5, 6, 7. We get up to, I'm going to skip those and go to octane. Octane is what's in your gas tank. That's why they give the octane rating, like 87 octane. It's the name was derived from that compound. Well, these get longer and longer and longer. Right? They form we usually draw a zigzag like that. See, 8. 1, 2, 3, 4, 5, 6, 7, 8. Any place at the end or where two lines come together is a carbon. I think I mentioned that last semester. And then, of course, carbon has 4 bonds, right? These are singles, so it has to have 2 more hydrogens here and here. Right? So each one of these carbons has a hydrogen on it. Well, the longer that chain gets, it's like the xenon. It's a big molecule. It has electrons here, and the bigger the molecule, the more likely they are to be redistributed one into the other as negatives and positives. Right? So when it does that, any neighboring molecule is influenced by that charge. And then when it does that, right, this pushes electrons away from it, makes that positive. Right? And this can happen anywhere in the molecule itself. I'm just doing it end to end for clarity. When it does that on a temporary scale, on a very, very instantaneous scale, you get those attractions. So the bigger the molecule, the higher the boiling point. And because you have more opportunity to form these London dispersion forces. Okay. Now there are other things involved here, especially with big organic molecules. You get entanglement. Right? They can just get wrapped up in each other. That's another topic. We're focusing on just the intermolecular forces right now. Okay, any questions? These chapters may look simple when you read them, but they really have some depth to them. And understanding this material frankly, it's difficult, especially when we start getting into 3-dimensional structures, right? How molecules arrange themselves. Right, so be sure and quiz me, and I'll try to explain it if something doesn't make sense. So melting and boiling points are properties dependent upon these intermolecular forces. Okay? The stronger the intermolecular force, the higher the melting point, higher the boiling point. And so if we decrease those, we go from dipole-dipole interactions down to London dispersion, we should see the boiling points and melting points decrease. And that's what we do observe, right? And it's like I said at the very beginning, right? Nature just does what it does. And we scramble to try to explain it. That's all science is, trying to explain what nature already does naturally. This particular slide is trying to demonstrate a trend. Okay, let's see, let's try this one, this top one. Hydrides of the chalcogens. So remember the chalcogens are here under oxygen. And if you start with the big one here and make a hydride out of it, it's going to have two hydrogens. Right? Because oxygen tends, these groups tend to be -1 charge or let's go blank. Oxidation states, excuse me. So they're going to have two hydrogens attached to it. So we use that because that eliminates a lot of the other variability. So the hydrides of tellurium, selenium, sulfur, and oxygen are listed there, and we're showing their boiling points. So the bigger one has a higher boiling point. And then we get smaller, the London dispersion forces say that the boiling point is going to decrease. Right? And we get down to the hydrogen sulfide, it decreases further. Then we get to water. Let's say, okay, what happened? Right? We would expect water to follow that dotted line right down here. Water should be down here if it follows the trend. Right? But instead of relying upon London dispersion forces and any slight dipoles that may exist, water now has available to it hydrogen bonding, which causes the boiling point and the melting points to go skyrocket, right? So and this happens for the nictogen group, the nitrogens, right? In all these that go up here, and then nitrogen, boom, it does the same thing. And then the halogens, right? And then when you get to fluorine, it goes boom, right? All those three have available to them hydrogen bonding. That's why they don't follow the trend. But if we have the carbon group, now hydrogen bonding is not an option. So the trend is more expected. It goes, the hydrides of tin, germanium, silicon, and carbon follow the trend. Right? And they're going to have 4 hydrogens with it. All right, so as you work your way down from larger to smaller, right, you decrease the boiling point, and methane is well behaved. Okay, that's the difference in those trends. It all has to do with hydrogen bonding of those nitrogen, fluorine, and oxygen compounds. Okay. All right. So that's the wrong button. There we go. Oops, I gave you the answer already. Which molecule is capable of forming stronger intermolecular forces? In this case, we're looking for what types of forces are available. Right? We know water has available for it hydrogen bonding, right, which is relatively strong. Whereas nitrogen, right, remember when we drew nitrogen Lewis dot structure? Right? It's a symmetrical molecule, no possibility for polarity. Right? So the only opportunity it has for bonding is London dispersion forces, which are very, very weak. So whereas water boils at 100 degrees Celsius, Nitrogen boils at minus 195 degrees. Right, that's the temperature of liquid nitrogen. We used to use that a lot to freeze plant material instantly. And I used to use it occasionally for demonstrations for school kids. You take something, I don't know, rubber balls were good. Take a rubber ball and submerge it in nitrogen, freeze it solid, pull it out with your tongs and throw it against the wall and it just shatters. You get lots of ooze and ahs. Or you could take a banana, freeze it, and of course, pull it out with a gloved hand and hammer a nail into a board. But the answer to that is the stronger forces are attributed to water because of hydrogen bonding, right? And that's the explanation. Okay, and keep going. Which gas would behave more ideally at the same conditions of pressure and temperature? Remember what we described as ideal behavior in gases in Chem 101. The molecules of the gas do not interact. Right? They don't interact when the pressure is low, the temperature is high. And what we're existing in right now meets those conditions. So which one would behave more ideally? The one that is less likely to exhibit any intermolecular attractions. Nitrogen is purely nonpolar. Its intermolecular attractions are all London dispersion, whereas carbon monoxide does have slight polarity, right? Oxygen is more polar than has a higher electronegativity than carbon. Right? Remember the trends? Yeah, oxygen's over here, carbon's over there. So oxygen is a higher electronegativity, which means it would be slightly polar toward the oxygen. And that would contribute intermolecular interactions or less ideal behavior. Right? So nitrogen would be the more ideal. And there's the explanation in blue and white. Okay, how about liquids? Well, we already know, we've learned that liquids have low compressibility, right? Which means what? Means there's not a lot of extra space between the molecules. Because when you compress, you're not compressing the molecule itself, you're compressing the space between the molecules. So liquids and solids both have low compressibility. Although we do know that liquids under extreme pressures will compress some. Right? Did I explain that last semester? They sampled water down at 2 miles in the ocean and found that it's more dense than the water at the surface. But they're not rigid. They cannot hold their own shape. And they have higher density than gases, densities that are in the same neighborhood as the solids. They do exhibit this property called surface tension. Surface tension is, by definition, a resistance of a liquid to an increase in its surface area. In other words, it doesn't want to get bigger. Liquids with large intermolecular forces tend to have higher surface tensions. Okay? Now, why is that? Well, if you look at the surface of a liquid and you have molecules here, here, and down here, doesn't matter what the molecules are, call it water if you want. Well, the interactions with the molecules are evenly distributed when you're in the middle here. Right? You got attractions here, attractions there, another one down here. Right? They're evenly distributed. But when you're at the surface, right, you still got that same force potential for the molecules, but the force potential has to be distributed under with fewer neighbors. Right? So you can only go here, here, and here. So that extra strength of attraction at the surface manifests itself as a resistance to increase, to be pulled apart, to increase its surface area. That's why when water drops are falling, they're roughly spherical, right? That's the minimum surface area is a sphere for a given volume. Okay, and you can see this demonstrated, surface tension demonstrated in nature, right? You ever seen a water skimmer? Little insects? No? Relatively calm water, and they've got, of course, they're insects, so they have 6 legs, right? They have 3 pairs of walking legs. So they're out there on the water, and you see them, they got their legs spread way out like this, right? And you see the water's dented a little bit, but they don't sink. They're using the surface tension of water to stay on top, right? And then a second later, they're gone. A fish comes, gets them. But you can see their legs moving so fast, they're just a blur, but they're moving across the water using that surface tension. So water has a very high surface tension because of its hydrogen bonding availability. Other molecules, other substances will have a low surface tension. In fact, it's the strangest thing I ever saw. Liquid helium in a dewar. You know what a dewar is? It's like a thermos bottle, only it's super insulated. It's silvered glass with a vacuum in between. And this particular one had an opening in the top, and it had liquid helium in it. And it's a demonstration in some lab. I can't remember where it was. But the helium climbed the walls and out on the floor. It had the lowest surface tension that I've ever seen. Right? It wanted to expand its surface area. Very low surface tension. It wasn't dangerous. It was just a small container of it, and it just out on the floor. So if you want to keep it in that container, you got to put a lid on it. Okay. Another phenomenon of liquids, which is due to these intermolecular forces, is capillary action. Right? Yeah, everybody know what capillary action is. A capillary is a very small diameter tube. Right? And if you take a capillary and put it in water, you'll see the water go up the tube a certain distance. And the smaller the diameter, the higher it'll go. In a capillary, actually in any container, but it's more evident in capillaries because the volume is related to the mass that's being pulled up, and mass only rises as far as the forces can sustain it, can hold it up against gravity. So the smaller the tube, the smaller the mass initially, and then you go higher because when you get up here on a thin tube, you get the same mass as you do on a thicker tube down here. Does that make sense? Maybe, maybe not. Okay, so you got your capillary. I'm going to expand the capillary, and you got your liquid here. And what you got is a competition between 2 types of forces. Right? The cohesive forces are those intermolecular forces that want to hold the molecules together. And the adhesive forces are the forces that are exhibited between the walls of the container and the substance. So if you've got things in here like that, and they're attracted to one another, they're also attracted to the walls of the container. So if the cohesive forces are much stronger than the adhesive forces between the substance and the container, then you won't get a capillary movement, right? Because what's happening is, for water, say, right? It always forms a meniscus like that. It forms that meniscus because at the edge, the adhesive forces overwhelm the cohesive forces. When you're out here in the middle, of course, the cohesive forces are stronger because there's more distance between them and the walls of the container, right? So that's why it forms that meniscus. And then in here, the cohesive forces win. Well, what's happening is when you put your capillary in the water, the force of attractions on the edges pull, and then the cohesive forces are pulled against that, and they pull themselves up, right? So it's like, it goes like this, and then it pulls itself flat, and then it goes, and then it pulls up some more, and it makes this, and then it goes flat again, right? And that happens so fast you don't see it. But eventually it gets to a certain height here, right? And the mass here is in a gravitational field, right? And the forces that are holding it up, the adhesive forces in opposition to the cohesive forces, have to be strong enough to support that mass, right? So there are cohesive forces all along here, and eventually you reach a balancing point, an equilibrium, where the adhesive forces minus the cohesive forces are just strong enough to hold up that mass, and that's as far as they can go. Okay. Now, if the cohesive forces are much stronger than the adhesive forces, and our example here is mercury. You ever seen a mercury barometer? Okay. If you're ever on the Greenbrier campus, go up to the fourth floor to the chemistry lab, and you've got a mercury barometer in there. You can see it, or you can look it up on the internet. So if it's mercury that you've got in here, you'll notice that the meniscus is that way. That's an indication that the cohesive forces are much stronger than the adhesive forces. Now, in a barometer, the only thing that's holding there up, the capillary action does not hold mercury up in this tube. What holds it up is air pressure, because up here is a vacuum, right? And air pressure is what holds it up there. But if you see a liquid in a container or in a tube, and you have a convex meniscus, then you know that the cohesive forces are stronger than the adhesive forces. In other words, mercury doesn't much care for glass, whereas water does care for glass, right? Everybody know what glass is made of? Well, it's kind of a complex mixture, but for all intents and purposes, glass is silicon dioxide. You got those oxygen sticking out there, and they have those two pairs of unpaired electrons, and they form a negative charge out here, and that's what attracts the water to the walls. If you put water in a different material, like maybe a plastic tube, you might get either be straight or maybe even convex. So there's a constant battle going on between adhesive and cohesive forces for these liquids. Here we go. Cohesive force wins for mercury. Adhesive forces win for water in a glass tube. Okay, they are dominant. Another physical manifestation of these intermolecular forces is viscosity. Everybody has a general idea of what viscosity is, right? You pour honey from a bottle, right? If it's at room temperature, it comes out kind of in a thick stream, right? Stick it in the refrigerator, and turn it upside down, it just sits there, right? The colder it gets, the more viscous it gets. Viscosity is a measure of a liquid's resistance to flow. And there are a number of ways of quantifying that value. And it depends on the liquid and the industry as to which one you use. For those food industries that are preparing, I don't know, say pudding, right? They would have a test for how viscous it is as an indicator of quality. Okay? And they would use, they usually use a squeegee plate. Right? They put a certain amount of material on a plate, and then they take a squeegee and run it, and it runs out, and then goes up here, and then runs out. Okay? And they measure the length. If it's thicker, then it'll run out quicker and be shorter length. Right? So that's one way to measure viscosity. Another way is to see how fast it flows through an orifice of a calibrated diameter. Like, a whole host of different ways. They can even use a penetrometer. It's a very thick liquid. They just drop this spiky thing. It looks like, everybody's seen a plumb bob. Right? Bricklayers use them, right, to keep their walls straight. It's a heavy weight on the end of a string, and it usually comes to a point. Right? You can drop one of those into your liquid, and how deep does it penetrate? That's an indication of viscosity. But it's all based upon this intermolecular force that is either thickening it or thinning the liquid. Right? The stronger the force, the thicker the liquid. And you can change the viscosity of liquids, like with the honey, cool it down, and then what that does is it reduces the kinetic energy of the molecules, which is used to overcome those intermolecular forces. So if the kinetic energy is lower, then the intermolecular forces are not disrupted. Right? So when you cool something down, you get a more viscous liquid. Okay. Now let's turn to solids. Solids can be divided into two categories. The amorphous solids are those that have a disordered structure. In other words, if you look at it on the atomic level or the molecular level, you don't see any order to the solid. An example of that is glass. Glass is an amorphous solid. Right? The molecules of the glass can be in any arrangement, right? There's nothing regular about them. Crystalline solids, on the other hand, have an ordered structure, and those are the ones that we're going to focus on for the next few slides, the next 15 minutes. Oh, no, 11:15. We've got 30 minutes now. We might be able to finish the chapter. And they're ordered in such a way that we can reduce them, right? We can chop them down until we get to the smallest unit that is repeated throughout the unit cell. This is one approach to describing a crystalline solid, is the unit cell. There are other approaches, but this one works fairly well. So this unit cell, like I said, is the smallest three-dimensional repeating unit in a crystal. But we can also use another model, and these two, the unit cell and this closest packing structure, the closest packing model, they're related to one another because they're based upon the same arrangement, right? Nature just does what it does and arranges these things in a certain way. And we can either describe it as a unit cell, or we can describe it as a closest packing model, right? And we're going to get into the weeds in a minute. Like I said, they're both related. These are, and the unit cell can be widely varying, but these are the three most common unit cells. The first one, and it's kind of hard to see that, the simple cubic cell. In this arrangement, you've got Let me see. Draw my cube here. You got atoms or molecules arranged only at the corners of that cube. And that repeats itself. And you see the ball and stick model just below it is how that would expand into a lattice. Okay. And then the space filling model at the bottom is actually, that's reality, where you have those atoms or molecules so close together that they touch. So if I were doing a space filling model, I would draw it out here big enough so that they would touch each other like that. And this is one of the simpler, simple cubic is very simple. And in the beginning, the best way to approach this unit cell concept is to use only pure metals, because they're fairly well behaved. This particular unit cell is characteristic of polonium. Now you didn't have to memorize polonium. Polonium is here. Right there. And it was, I think it was named in honor of the Curies, either Marie or her husband, because they were both from, well, she was from Poland. Right, so they called it polonium. They worked with it's radioactive. And of course, you all know that Marie Curie won the Nobel Prize for her work in radioactivity, but she paid the price for it in the long term. She developed cancer. They didn't realize just how dangerous radioactive materials are. Anyway, that's one way to draw the unit cell in that simple cubic form. We can also keep these atoms. Well, let's just, if we're talking about metals, we say there's an atom here, 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 here. There's 6 of them in that unit cell. We can also put one in the middle, in that space that's in the middle of the cube. And when we do that, that tends to push these guys apart, right? Because they can touch the one in the middle, but then they're pushed so far apart, there's a gap between them on the apexes of cube. Okay. Another possibility is, let me draw another one. Another possibility for this cubic structure is if we have atoms at the corners like we did before, but instead of putting one in the center, we put one on the face of each of the cubes. Right? So how many faces are there on a cube? 1, 2, 3, 4, 5, 6. 6 faces on the cube. So we can put one on the face of each cube. Okay, and that's another face-centered cubic cell. And this one would be a body-centered cubic cell versus a simple cubic. Now, why is it important that we know this besides just pure scientific curiosity? If we know the unit cell structure, we can say something about the overall, some various physical properties overall of the substance itself. In other words, how many atoms are assigned to each unit cell? Right? And what they've done there in that bottom is they've shown you what part of the atom is assigned to that cubic cell. Of course, if it's in the middle of the cube, that whole atom is part of that cell. But if it's at the corner, those corner atoms are sharing with other cubic cells. Put that on tight enough. So how many atoms are assigned to each of the simple cube versus the body-centered cube versus the face-centered cube? Well, if it's a simple cube, then how many other cubes is one of those corners being shared, right? You've got one up here, You got one over here. You got one in the back. You got one over here. Actually, you got one back here. You got one in the front. So what we find is that for each of those corner atoms, only 1/8 of each atom is part of that simple cube. How many of them do we have? Well, there are 8 corners, aren't there? 3, 4, 5, 6, 7, 8 times 8 equals 1. So there's one atom in our example for metals, one atom per simple cube. Okay. If we have a body-centered cube, we still have this one atom, right? From this arrangement, but we've got this one in the middle plus 1, so we have 2 atoms per unit cell for the body-centered cube. Okay. How about for the face-centered cube? Well, we've still got the one atom from the corners, but how many do we have for the face centers? Well, let's say we have 1, 2, 3, 4, 5, 6. We've got 6 faces, and each face has a half an atom, right? Because it only faces one other cube. So half of it belongs to that. Times 1/2 is what? 3. So 1 plus 3 equals 4. 4 atoms per cell. Right, so you got 1, 2, and 4 for those models. Now, what type of problem could we solve with this? Well, if we know that the atom is polonium, right? We know polonium is 84 grams per mole. 84 grams for 6.022 times 10 to the 23rd atoms. Right? If we know how many atoms are in a cubic cell, in its unit cell, then we say, how much does that one atom weigh? Right? And then we say, how many unit cells do you have? And you can determine the density. Right? What we need to do now is to have a formula for what's the volume of the unit cell. Then we could determine density, because we know by how many atoms are in the unit cell what the mass is, and then if we can tell the volume of the unit cell, then we can determine the density. So what would be the volume for the simple? Right? If we have a simple unit cell, simple cube, where this one is touching that one, what's the volume of a cube? It's the side of the cube cubed, right? Height, width, breadth, height, width, length. Right? So we know that the volume is r cubed. So what's r? Right? Well, the radius. This is the radius. I probably should have made that maybe a. The radius here and here are exactly the same. So the side of the cube is actually 2r. The radius of the atom. So if we know the radius of the atom, right, size of the atom, which we can look up, then we just need to cube it. And we have the volume of the cell. Okay? There are other formulas for these, right, for this one and that one. They're a little more complicated, but they should be useful information. Okay. So I spent too much time on that. Let's let this video run. And come on. There we go. Is it going to run? There it is.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, Covalent compounds and, as you'll see in the next two examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
Okay, we got into a little bit of the closest packing model there, and hopefully saw some relationship between unit cells and the closest packing model. A good way to approach it is to consider how much space is being used by each of the models. It turns out that the body-centered cubic uses, what do you say, 74% of the available space, whereas the simple cubic only uses about 52 or 58%. Now, there are other factors that go into forming these different structures. Some could be as simple as electrostatics, like sodium chloride forms that body-centered cube. And very often, a good approach is to look at the largest partner, right? So we would take the chloride for sodium chloride, say, how does it fit together? And then the sodiums go into the spaces that are left over, right? So it can get complex pretty quick. And I'm going to try to avoid too much complexity because we just don't have time to deal with it in this course. But I've got another one coming up, another video coming up. I'm not sure if there'll be enough time to view it. No, we'll have to save that one for next time, talking about the closest packing model. But I do want to get into some analytical work next. How do we know what are the distances between? How do we know anything about the way that these layers form, the way that the unit cells form? Fortunately, there was work done by Bragg, and I think his son was part of the team too. And they developed this equation called the Bragg equation, and there it is on the board. The n is just any integer, 1, 2, 3, 4, whatever. And lambda is the wavelength of the X-rays that you're blasting at your crystal. And you're shining these X-rays at the crystal at a given angle. Okay, so that's what the theta is. And the d is the distance between the layers. What they're doing with this equation is quantifying the effect that the crystal structure itself has on the diffraction of the X-rays that bounce off the crystal. I use this particular method to determine the layer distances in soil clays, because they're very regular structures. And I would go through a procedure of separating the sand and the silt from the clays by simple sieving. And then we'll take the clays and distribute them in a graduated cylinder in a phosphated solution, which helps keep the particles separate from one another. They don't clump when you do that. And I would use another relationship. I forget the name of it for the moment. But we would know that once you mix it up and let it settle, that after a certain time, you know that at a given depth, you would have only the clay particles and nothing else. So I would dip my probe down there and suck up some of it and put a drop on a microscope slide, let it dry. And as it dries, those clay particles are plate shaped. So they would orient themselves and they would lay flat once they're dry. You know, stick that in the machine and scan through angles with x-rays of a known wavelength. And you would get this, it would come out at peaks. And each of those peaks represented a change in that N. N equals 1, equals 2, equals 3. They're like, does anybody play a wind instrument? No. Well, you can do this with a simple, like French horn, for instance. You can blow at a certain pressure and you'll get a note. And if you blow harder and tighten your lips further, you get the next one up. You get harmonics. That's the idea here. With that one, you're getting the fundamental, next, second harmonic, third harmonic. And with this information, the angle that gives you the strongest reflection, and then another angle gives you a strong reflection, but it's a little bit less than the fundamental, then you can determine the distance between those layers. Right? That's the idea behind the Bragg equation. Let's see if I got it. Yeah, there we go. So those dark dots are the atoms. Oops, sorry, wrong direction. Are the atoms in the crystal structure. Here it is. Right there. And they're layered. Right? Now, this shows that they're layered on top of each other, but they don't have to be. Right? They could be offset into the gaps between them, just like we saw in that previous video. And when you shine the incident X-rays, we have to use X-rays because the distance between the two layers is very small. So we use a very small wavelength light, and that's X-rays. And here's the theta, this angle of incidence. And you got one that bounces off this layer, and this one bounces off the next layer. And the distance determines whether or not the interference of this one with that one is going to be constructive or destructive or somewhere in between. So when it's totally constructive, then you get an increase in intensity, and you can detect that as you rotate the angle of incidence. It's just everybody's eyes are starting to glaze over. Was this part of first semester at WVU? No. Okay, they didn't get to this part. Okay, that's good. You know, let's sit through a second lecture on it. Now, that works great. In my case, when I was just dealing with clays and all I wanted to know was the distance between the layers, that was how we classified the clays. So I knew what type of clay was in my soil that I was studying. But if we do this in a three-dimensional environment where you have the crystal and the X-rays are actually shown through it, then you get a different type of constructive or destructive interference, and we get a three-dimensional, or actually a two-dimensional pattern on a photographic plate. Here it is. It's not behaving. I can't point. Anyway, you see that pattern, and with experience, a technician that has done lots of these and had training can interpret those patterns to tell us what the crystal structure is in that crystal. In fact, this is the method that was used to elucidate, to determine the crystal, the molecular structure of the DNA molecule, to prove that it was a double helix. And it was much, much more complex than that. It took months and months to tease out the structure of the DNA molecule. The first problem was, how do you get something that's a big, long strand into some regular arrangement so that you can use this crystallography, right? Because it's normally amorphous, right? So that was the first trick. Okay, so now we'll move away from that for now and talk about different types of crystalline solids. Right, we had atomic solids we talked about before with our unit cells. Those were the ones where we used metals as our atoms. But you can have crystalline structures composed of molecules as well. They're discrete covalently bonded molecules at each of the lattice points, or in the body, or on the faces of the cubes. Or you can form them from ionic solids, in which case you usually take the larger, the anion, is typically the larger one, and you say, all right, this forms a certain structure, and then we put the cations in the spaces. And you put them in the spaces that will give you a neutral charge for the unit cell. Right? If it's sodium chloride, you only need 1, 1. But if it's calcium chloride, you need 2 chlorides and only 1 calcium in there somewhere, with its closest neighbors to neutralize its charge. All right, so here are examples. Right. What type is diamond? Diamond is a crystalline lattice that's formed by covalently bonded carbon atoms at every point in the lattice. Right, there are no intermolecular forces that we need to worry about. They're all intramolecular. They're all covalent bonds. In fact, if you have a perfect diamond and you could shrink yourself down small enough, you could skip from 1 carbon atom, and as long as you follow the bond, the covalent bond, 1 carbon, 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 you could go from one side of the diamond to the other side and always stay on a carbon. Right? It'd be one continuous. It was kind of like the original explorers of the United States. When they first started trying to move into the interior, it was one solid forest. It was just one tree after another, and until they broke out into the Great Plains, right? But in the eastern United States, it was just one solid forest. Anyway, so that is a, let's see, there it is. The covalently bound diamond. The ionic solids, like sodium chloride, tend to form lattices where you have neutralization of the charge, and you have the cation situated in the spaces between the anions, because they're the bigger, usually the bigger. Right? This would be an ionic solid. Then you have molecular solid. In this case, we have hydrogen bonding, and they're using ice here as the example. And you notice the hexagonal structure. Check and get this thing. Here it is. Ooh, it's coming down. There it is. So there's your hexagon right there. And that's a well, the diamond is an example of a network atomic solid. And the, oops, okay. The metals, these are all atomic solids. Diamond, metallic, and the group, the AA is the noble gases. Those are atomic solids. Then the molecular solids, our example was what was water. Dipole, and London dispersions are the forces holding them together. And the ionic solids are purely electrostatic between complete ions holding them together. Okay. That's it. This is a good place to stop. Because the next thing we're going to get into is try to understand solids from the standpoint of closest packing model. I'm going to make myself a note here, and this will be on the 25th, 5/25. Where we'll pick it up. And let's see, we'll finish chapter 10, and then let me see how many. We should be able to do it. Yeah. And if we can't finish it, chapter 11, then we'll just glide into the buffer day. Okay. Any questions? Any problems that I've presented that you want to talk about? Okay. So what things did I repeat here that you've already covered? Just at the very beginning?
Yeah.
Yeah.
Most of it except the Bragg equation.
You didn't talk about that. Okay. There are problems in the review document using the Bragg equation. So you can get some practice with that. Problems that you can practice.
Oh, okay.
Yeah, using the Bragg equation. Okay, and you can start working on your crossword puzzles. Oh, I will say this about the crosswords. If the answer is 2 or more words, there won't be any spaces. You just run them together. Okay. All right. So I know that would give you fits if you're trying to stick a space in there and there's no place for it.